Hi everyone, I'm Ke Pei, a fifth-year PhD student at Columbia University. Today I'm going to present our paper, XDA Accurate, Robust Disassembly with Transfer Learning. This paper is done with my wonderful collaborators Jonas Guan, who is the co-first author, David Williams King, and my two advisors Junfeng Yang and Suman Jana. Disassembly, which is always the first step in any binary analysis or reverse engineering tasks, is the fundamental building block for many downstream security-critical applications. The applications include retrofitting control flow integrity defenses, vulnerability detection, malware analysis, and binary hardening, to name a few. By definition, disassembly is a process of recovering high-level constructs from binary code. For example, given a sequence of raw bytes from binary code, disassembly aims to recover the assembly instructions, function boundaries, source-level data types, or control flow graph. However, disassembly for stripped binary is fundamentally challenging because high-level information such as symbol tables are often stripped away for most of the real-world binaries. Therefore, disassemblers must approximate the recovery of higher-level constructs from incomplete information. In this paper, we focus on two disassembly tasks. The first task is to recover function boundaries. For example, given a sequence of raw bytes of a binary program, we aim to identify the function boundaries such as the function start and its corresponding function end. The second task is to recover assembly instructions. Similarly, given a sequence of raw bytes of a binary program, we aim to recover the corresponding assembly instructions. As disassembly is the basis and prerequisite for any downstream binary analysis and reverse engineering tasks, all well-known off-the-shelf reverse engineering tools have the built-in support for disassembly. Examples include IDA, Ghidra, and others. Besides mature and reverse engineering tools, disassembly is also heavily studied by an extensive number of research papers, generating many research prototypes. Due to the nature of uncertainty in the disassembly process, machine learning and statistical analysis have shown increasing promises in the recent years. Despite significant effort, existing works and tools still suffer from the following limitations. The first well-known limitation is they are not accurate, especially when the binary is compiled by certain compilers that further complicates the disassembly. Consider the following binary code extracted from Vim 8.2 compiled by MSVC 2019. The ground truth disassembled assembly instructions are shown side by side. Consider the red highlighted part, which is a data section interleaved with code, representing a few jump table entries. Unfortunately, OBJDump translates the bytes from the data section as code, resulting in false positives. The inherent reason is OBJDump linearly disassembles a block of bytes by assuming all of the bytes are part of the code. This assumption fails when the compiled code and data are interleaved. Now consider the blue highlighted part, which demonstrates a case of function beginning. This time, the well-known tool Ghidra treats the actual code as data section, which fails to translate it into the correct assembly instructions, resulting in a false negative. The inherent cause is most of the state-of-the-art disassembler follows the control flow of the program and disassembles the part that are only reachable in the control flow graph. However, statically recovered control flow often struggles with indirect jumps and calls. Therefore, here Ghidra fails to identify this indirectly called function. Existing approaches also construct a large set of heuristics for disassembly. However, these heuristics are often brittle. For example, consider another byte piece extracted from the same program, which exemplifies a typical function prolog pattern. We find that when we increase the compiler optimization, the function prolog pattern disappears. As a result, both the non-ML-based tool like IDA or ML-based tool like bidirectional RNN fail to recognize the optimized function. Moreover, it has been shown that the previous ML approaches are evaluated on highly overlapping training and testing set, where their reported result might due to overfitting. Finally, a lot of existing tools rely on manually constructing heuristics for disassembly by domain expert. This database of patterns need constant maintaining and updating. For example, both IDA and Ghidra maintains a large pattern database that needs to cater to new compiler idioms or new architecture specifications frequently. In this paper, we propose XDA, an accurate, robust disassembler based on transfer learning. It is accurate. Our extensive empirical studies show that it achieves 99 and 99.7 F1 score, respectively, in recovering functions and assembly instructions, outperforms the state-of-the-arts by 17.2 on average. It also remains robust, achieving consistently high accuracy across different compilers, operating systems, architectures, optimization levels, obfuscations, and more importantly, on different training and testing overlap rate, including those that are strictly non-overlapping. Finally, it is automated. We leverage novel, unsupervised self-training to learn robust features useful for disassembly without any manual encoding features or creating heuristics. This implies that we can cheaply collect a huge number of training samples in the wild. As a task recap, we focus on recovering functions and assembly instructions from the raw stripped binary. Both tasks can be formulated as recovering boundaries, which can be easily set up as a classification task for each token. Such a formulation makes sense, as the instructions in x86 has variable length, so if we can correctly recover the boundary of each instruction in the raw bytes, translating the bounded bytes to corresponding assembly instructions is just a one-to-one mapping. Our key insight is to teach the ML model general dependencies between bytes in machine code before training it to perform specific disassembly tasks. Intuitively, we first teach our model to read and gain a basic understanding of machine code and then transfer the learned knowledge to solve a disassembly task. Specifically, consider the following sequence of bytes. In the first stage, we pre-train our model using masked language modeling to teach it the byte dependencies. The masked language modeling task asks the model to predict randomly masked bytes, which requires the model to produce missing bytes given the context. In the second stage, we fine-tune our model to leverage its learned knowledge of byte dependencies to solve a specific disassembly task, such as predicting function start and function end. Here we elaborate more on the intuition on why masked language modeling helps the model to learn machine code semantics. Consider the same raw bytes extracted from Vim 8.2. Now consider its instruction sub-RSP 28 bytes that decrements the stack register by 40 bytes to allocate space for local variables. Now assume the byte part is masked. In order to predict it, the model is forced to understand the semantics of local variables allocation and search in the context of later usage of allocated local variables. Since such an operation often happens at function prologue, learning this knowledge can be useful to detecting function start. Now consider the jump table example shown in the bottom, where we mask out the partial jump table entry 77 and 33. In order to predict the masked bytes, the model is forced to distinguish inline data from code. Specifically, it has to understand the semantics of return instructions, which likely remarks the function end, and how jump table entry is accessed in the context in order to infer the correct value and eliminate other potentially correct instructions. Such scenarios that naturally occur in predicting randomly masked bytes altogether teaches the model a powerful general understanding of machine code semantics that helps disassembly. In order to efficiently learn dependencies between bytes and to understand the machine code semantics, we employ self-attention layers in the model architecture. This design is shown more capable than the sequential connections in RNNs in capturing long-range dependencies between distant bytes. Specifically, in pre-training, Given a sequence of raw bytes, the self-attention layer computes the attention magnitude between every pair of byte tokens. We then stack multiple stacked self-attention layers to aggregate information of the context. We then train the stacked self-attention layers to predict the masked bytes end-to-end, forcing them to learn how bytes in the context interact with each other, in which the machine code semantics manifests. After the model is pre-trained, we keep the pre-trained weights and transfer the learned knowledge for training on disassembly task. We developed the masking strategy with random span. Specifically, we randomly chose different span of bytes to mask in the input sequence. The span size can vary from 1 to 3. Such a treatment creates different scenario that compels the model to learn different aspects of machine code semantics. Moreover, we fix the total number of masked bytes to account only for 20% of the total bytes in the input. Such a treatment ensures the task not too hard, otherwise it is impossible for the model to learn any meaningful knowledge. We plan to study how varying masking percentage affect our model's performance in both pre-training and fine-tuning in our future work. We collect extensive dataset to evaluate XDA from different operating systems, compilers, architectures. We also keep our training and testing overlapping rate minimum. This is to address the concern raised by the study of Andresi et al., where the evaluation set of previous ML-based approaches has high training and testing overlapping rate. We compare XDA to 5 representative baselines and use precision, recall, and F1 score to evaluate the prediction performance. These metrics make more sense than the accuracy, as the label distribution of both tasks is highly unbalanced. The number of boundaries is much smaller than that of non-boundaries. We average the F1 scores achieved by XDA and other baselines on all datasets. We find that XDA achieves 17.3 higher F1 score than the second best tool. Moreover, we notice that OBJDump has very high F1 score, but it is just because the number of cases of inline data makes up only a tiny fraction, which is less than 1% in our dataset. But OBJDump consistently fails to distinguish inline data throughout all of our dataset. Besides the general accuracy, we also evaluate the robustness of XDA. Specifically, across different optimizations, XDA remains high testing F1 scores, while we can see that bidirectional RNN struggles with more aggressive optimization level. Very interestingly, we also observed that the pre-trained XDA reaches over 95 F1 score within the first training epoch, while BiRNN struggles to have only 0 F1 score within first 10 epochs. We evaluate XDA's inference time on both GPU and CPU and compare it with IDA and Ghidra, two non-ML based tools. We observe that XDA running on GPU is up to 38 times faster than IDA and Ghidra. We also conduct ablation studies to show the effectiveness of pre-training. We find pre-trained XDA outperforms that when it is not pre-trained by 11.7 F1 score. Moreover, we find that even without pre-training, which means XDA is also trained from scratch, just like bidirectional RNN, it still outperforms it after 30 epochs. This implies our model architecture alone is more effective for disassembly, likely due to the adoption of self-attention layers. In summary, this paper introduces XDA, a new disassembler based on transfer learning. It introduces a novel pre-training stage to train the model to learn machine code semantics before training it to perform downstream disassembly tasks. We have intuitively and empirically shown that such a pre-training strategy helps the model learning effective and robust features instead of learning spurious and brittle patterns. Moreover, since the pre-training task is fully unsupervised and automated, it significantly saves the expensive manual effort in maintaining heuristics and can be cheaply trained from large-scale binaries. We have empirically demonstrated our approach is effective, outperforms the state-of-the-art by a large margin. Finally, we have made the code and dataset public. Thank you.